Hello students, good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week's we are revising properties of matter, mechanical properties of matter, and we have already covered viscosity, and in yesterday's class we started surface tension. This second lecture of surface tension will be final and concluding one, and in this lecture we will cover excess pressure inside the soap bubble, and then we will look into the cohesive and adhesive forces, and we will define contact angle. Okay, and we will also look into the calculation of contact angle, and thereafter we will be discussing capillary rise, and if time permits we will also look into some problems of surface energy. Okay, so here, without losing any further time, let me share my screen with you guys. So here we go. In yesterday's class we already discussed that the pressure difference across a curvature, okay, having two radii of curvature, is given by sigma into 1 by r1 plus 1 by r2. Okay, where r1 and r2 are two different radii of curvature, and sigma is nothing but the surface tension of the fluid. Okay, and now from that we derived that result, we established that result, that first case, if we have a liquid drop. Okay, so in that case r1 will be equal to r2, let's say will be equal to r over here. So this is p in and p out, and we also discussed that the pressure at the concave side of the curve will be greater than the convex side. So pi minus po, which is nothing but delta p excess over here, that will turn out to be 2 sigma by r. And if we have a liquid bubble, so we realize that bubble has two interfaces. Okay, like for example, here there was air, and here there is liquid, and here there is air again. So there are two interfaces, two curves over here, and if inside pressure is pi and outside pressure is po, so pi minus po, which in this case will be the excess pressure. Okay, and that will turn out to 4 sigma by r, that we looked already in previous class. Now let's take some problem based on that concept. And a very famous problem is this one. Let's say we have two soap bubbles of different radii, let's say r1 and r2. Okay, and obviously we can see that r1 is greater than r2. If these two soap bubbles combine with each other, okay, what will happen? This is one of the soap bubble, and that is another soap bubble. They combine, so they will be forming a common interface. Okay, and this common interface, you must realize, will be having some radii of curvature. So the radii of curvature of this surface we know, that is r1, and this surface we know r2. So what would be the radii of curvature of this interface which has been created between these two soap bubbles of different radii? So what we must realize, since this is the larger bubble, so the pressure inside this larger bubble, you can say like P1, let's say, and I will be writing the gauge pressure over here. That will be pressure in excess to atmospheric pressure. So outside pressure is atmospheric pressure, so the gauge pressure outside is 0, and P1 would be in how much excess? That would be simply, we can write it as 4 sigma by r1, and here you must realize inside this soap bubble P2 will be equal to 4 sigma by R2 over here. And since R1 is greater than R2, you can clearly see that the P1 would be less than P2. P2 would be greater than. So here, this side the pressure is more, this side the pressure is less. So obviously this would be the shape of this interface. Means the smaller bubble side would be the concave side and the larger bubble side will be the convex side over here. Okay. And from this pressure difference, since we already know that the pressure difference across this surface would be, you can say if the radius of curvature of this part is r, so this pressure difference, which would be P2 minus P1, that got to be equal to 4 sigma by R. Why this 4 term is here? Because see, this will again be having two interfaces. So P2 minus P1, the value of P2 and P1 already we know. So that would be simply 4 sigma into 1 by R2 minus 1 by R1, and that will be equal to 4 sigma by R, and 4 sigma will get cancelled. So solving for R, we will be getting as R1 R2 divided by R1 minus R2. So this would be the radii of curvature, radius of curvature of the common interface, this interface over here. And let's look at other interesting points of the geometry of this situation over here. There are a few things which might be interesting to you guys. So let me draw that picture again. Okay, so this is one, and say this was the another soap bubble, and here we had some this surface. So understand, like this curve which I have drawn, this curve which I have drawn, and this curve which I have drawn here. Okay, you must realize that they are the part of curve, and basically these line indicates which I have drawn is on the plane of this paper over here. So if we consider a small segment of liquid over here of, let's say, dl length, so that will be experiencing some force in this direction due to surface tension of this surface that would be tangent to this surface, and this would be nothing but sigma times dl. And along this surface it would be again experiencing sigma times dl, and along this surface it will again be experiencing sigma times dl over here. So now you must realize this molecule of let's say this element of liquid of small length dl is experiencing three equal forces in these directions. Okay, and the resultant of these forces must be equal to zero, because this element here is in equilibrium. So that is possible only if that the angle between these forces which we have indicated is equal to 120 degrees. So all these angles here are 120 degrees. So that is one of the interesting fact. Okay, so please understand this line, this curved line, this curved line, and this curved line I have taken in this plane. So all these angles between them is nothing but 120 degree, because this value of sigma is constant. This whole thing is made up of same soap solution. So sigma is constant over here. So this is one interesting phenomena. Another interesting phenomena I want to tell you about, let's say the center of the larger bubble, let's say that is C1, and the center of the smaller bubble, let's say that is C2. Okay, and let's say this point, this common point here is point P. Okay, and if we join C1 with P and we join C2 with P, okay, and this angle over here, this side C1 C2. So now we are interested in finding out like C1 C2, what would be the length of C1 C2, and that is equal to D we want to find out. So in order to do that, we need to look into this triangle C1 P C2 over here, and you should realize first of all this line over here is tangent to this surface, so this is 90 degree, and this line over here is tangent to uh, this surface, so this will be making 90 degree with the radius. So this is 90, this is 90, and this is 120 over here. So that clearly gives this angle over here, that is angle C1PC2, that is definitely equal to 60 degrees. So this angle here is 60 degree over here. So now it is very easy for us to find out the value of C1 C2, which is D, because the other two sides we know that is nothing but R1 and this is nothing but R2, and the angle between them is 60 degree. So in order to find out D, we can use the cosine rule. So D will be equal to simply, that would be R1 square plus R2 square minus 2 R1 R2 cos 60 degree we can write, and the under root of this thing. Okay, and 60 degree is the angle, this angle over here. So obviously cos 60 is nothing but 1 by 2. So this will turn out to be R1 square plus R2 square minus R1 R2 root under over here. Okay, so the distance between the center of the two bubbles we managed to find out. And another thing uh, I want us to realize is this thing. So you can see that the bulging here of this curve is towards the towards the larger bubble over here. So here, this cross section, this would be some cross section, and I wish to find out the radii of curvature or the radius of this cross section. Let's say this is A, this is A. Should I draw another diagram, because this diagram has already become messy, so I must put it another diagram. Okay, something like this. Okay, and this was another surface. So this bulging, I want to find out the radius of this cross section. Okay, I hope you are able to imagine the three-dimensional view of this picture. Okay, so this thing I want to find out. Let's say this is A. Okay, and we have already looked into the other part of geometry. Like, let's say this was C1, this was C2, and this, let's say this point O will be lying here, and this is nothing but R1, and this is nothing but R2, and this C1 C2 we have already got it as D. The value of D we know, and this length A we want to find out. So for example, let's say this is theta. So using sine rule in this triangle, we can definitely write that would be sine theta by R2 will be equal to, this angle was 60 degrees, so sine 60 degree divided by D. Okay, so that gives us sine theta is equal to R2 times, and sine 60 degree would be root 3 by 2, and in denominator we will be having the value of D. We obviously know this is the value of D. So once we have got sine theta, now looking in this right angle triangle, over here, this length A, we can surely say that this A is nothing but R1 times sine theta. So that would be nothing but, what we can say, that would be root 3 by 2 into R1 R2 by D, and the value of D, let's substitute over here, that would be R1 square plus R2 square minus R1 R2. So this would be the value of A. Or alternatively, in many situations, the ratio of R1 and R2 is given to us in a given question. So it would be better to represent this in form of the ratio of R1 and R2. Okay, so for example, R2 by R1. So if we divide numerator and denominator by R1, what we will be getting is that it would be R2 divided by 1 plus R2 by R1 square minus R2 by R1 over here. So this will be the expression. Whichever form you are comfortable with, you can use that. And now, being said that, let's look into some special cases after that. Okay, some special cases here. So first special case, if the size of both the bubbles are same, say R1 is equal to R2. So first of all, you must realize the radius of curvature of the common interface is gonna be equal to infinity, because we remember, no, like R R is equal to R1 R2 divided by R1 minus R2. So this denominator will become 0. So the radius of common interface will become infinity, means that surface will become flat. This will look something like this. Okay, this surface will become flat, as you must realize the pressure from this side and the pressure from this side are equal anyway. So this surface will become flat. What would be the value of A in that case? The value of A in that case, when you will be substituting things over here, like the value of R1 and R2, when you will substitute, what you will be getting is, let's say R1 is equal to R2 is equal to say R0. So after substituting, you will be getting root 3 by 2 into R0 over here, means this radii, like this thing, you will be getting this quantity. This would be A. Okay, so this is one of the special case. Another special case we can look into also, like for example, if R1 is much greater than R2, like one of the bubble is very large, okay, and the another bubble is very small, something like this, you must understand. So in that case, you should realize that R will be approximately equal to R2, like substituting R1 much greater than R2, then this denominator will be approximately equal to R1 and R1 will get cancelled. So R will tend to R2, means like this bubble will be something like this over here, you must realize. And when you will be substituting like for example, in this expression which we have derived, if we substitute R2 by R1 is nearly equal to 0. So what we will be getting here is A will be simply equal to, A will be tending to, you can say, root 3 by 2 R2 over here. So this is the second case. And one another interesting case, let's look into the third special case. If R1 is equal to 2R2, in that case you should realize that R will be simply equal to R1 and A will be equal to R2. That you should realize. So these are a few interesting things you can look into. And now let's move on to the next discussion. So now let's discuss about cohesive and adhesive force. So first let's talk about cohesive force. So you must realize that is the force of attraction between liquid molecules of same substance. For example, liquid interaction, or gas interaction, or solid interaction. You must also realize that the force of cohesion is very large in case of solid. Okay, so that is why solids have a definite shape. On the other hand, the force of cohesion in case of liquid is weaker than that of solids. Hence, liquids do not have definite shape but have definite volume. And you must also realize that the force of cohesion is negligible in case of gases. Because of this fact, gases have neither fixed shape nor volume. So like basically cohesive force are responsible for the definite shape of solid and definite volume of liquid, whereas in case of gases neither has a fixed shape nor volume, you must realize. Okay, so a few examples of a cohesive force is like two drops of liquid coalesce into one when brought in mutual contact because of the cohesive force. And the secondly, you can also say that it is difficult to separate two sticky plates of glass wetted with water because of a large force. Okay, like this situation we have already seen in one of the previous examples. And for example, you might have realized that it is very difficult to break a drop of mercury into small droplets because of very large cohesive force between the mercury molecules over there. And secondly, now let's discuss about the adhesive force also. So adhesive force basically This one was cohesive. Let's write it over here, cohesive force. And the secondly, adhesive force. About adhesive force, you might be knowing that already. That is nothing but the force of attraction between, we must not write liquid over here, that simply is molecules of same substance. So the force of attraction between molecules of different substance, like for example, if two different substances will come into contact with each other, the molecules in contact with each other will attract each other with the help of adhesive force. Okay, so let me give you some example of adhesive force. Adhesive force, you might have realized, like when we write with the help of a chalk on blackboard, like we are able to write because the molecules of chalk are attracted to the molecules of the board. So that is why we are able to write, due to the adhesion between the chalk and the blackboard. Other example, like for example, we write on paper with some ink, so there is a adhesive force between the liquid molecule of ink and the paper. And also you must also have noticed that large force of adhesion between cement and bricks helps us in construction work also. And like for example, fevicol or gum are used in gluing two surfaces together, because see, like that provide a large adhesive force. So this is, you should realize, so that is cohesive and adhesive forces. So now let's talk about something called angle of contact. Angle of contact, or simply you can say contact angle. Okay, so angle of contact, the angle which the tangent to the liquid surface at the point of contact makes with the solid surface inside the liquid is called angle of contact. You must realize. Let me demonstrate it with some examples over here. So I'm taking the first example. Okay, so let's say this is a solid surface. Okay, and liquid is filled from one side. You must realize, let's say this is liquid. So here you can see, okay, that liquid is coming in contact with the solid over here. So how are we going to define this contact angle? So this is the point of contact. So here, let me use another color pen. Here I am going to draw a tangent on the surface of this liquid over here. This is the tangent. And another thing you must realize, that is the solid surface inside the liquid, and the angle between these two lines will be known here as contact angle. Okay, contact angle. So here you should realize that theta is less than 90 degree, or you can say acute angle. And here this combination of liquid and solid is known as wetting combination. This is wetting combination. And let me take one another example here also. Let's say, for example, second example, let's say this is our solid surface, and let's say the liquid is like that. Now you see, this is the liquid, and here this is the point of contact. So if we draw a tangent on the surface of liquid, this would be like this, and the solid surface inside the liquid would be this. So this angle here would be contact angle, and you should realize in this diagram, the way I have drawn it, like theta is equal to 90 degree over here. And we must also look into a third situation, okay, where angle of contact would be an obtuse angle. Let's say, for example, this kind of case scenario. So this here is a point of contact, and here when we will draw the tangent on the surface of liquid, okay, and this is the solid surface inside the liquid. So here this is angle of contact, and here you should clearly realize that theta is greater than 90 degree over here, and this combination is non non-wetting combination. Okay, that is nothing but non-wetting combination. Another way to look into contact angle thing, like for example, if you put some liquid drop on a horizontal surface, let's say fourth example, if we put some liquid drop on the horizontal surface, it might either get spread, okay, or it might not spread on the surface. Like these two possible things could happen. Okay, so here will we be able to look like how the contact angle, which angle we can say is the contact angle. So the idea is very simple. We must follow the same definition. Let's say for example, this is the point of contact. Okay, and here if we draw a tangent on the surface of the liquid, this would be the tangent, and the surface of solid inside the liquid is this one. So this here is angle of contact. Okay, so theta here also you can see that is less than 90 degree or acute. So this is a wetting combination, whereas in this picture this is the point of contact. So when you will draw a tangent over here, and this is the solid surface inside the liquid, so this here would be the angle of contact. So theta definitely here is greater than 90 degree, so obtuse angle. So this here is a wetting combination, and this here is non-wetting combination. Let me give you some data also, like for example, the angle of contact, two important data you must know. Like the first one is angle of contact between let's say pure water and glass. For pure water and glass combination, the angle of contact is 0 degree. And the another data I'm going to give you is the angle of contact between the combination of mercury and glass. Okay, and that nearly is equal to 135 degrees. So this is acute angle. So you must realize pure water glass surface would be a wetting combination you can say, and the mercury glass combination would be a non-wetting combination. Okay, here the angle of contact is an obtuse angle. So here we are geometrically able to see like how will the contact angle look like. And now let's try to find out like how we can calculate the contact angle. Okay, so calculation of contact angle. Okay, so now for example, let's take this picture over here. So this is the picture, this is the liquid, and this here is the solid surface. And you must realize here that not only solid and liquid are in contact with each other, this media is gas. Okay, so basically we are looking at three interfaces. This interface is the solid gas interface, and this interface is liquid gas interface, and this interface is solid liquid interface. Okay, so whenever, like for example, if this drop has been put on this horizontal surface over here, so here there was only liquid gas interfaces. So when it has been dropped into the onto the surface, new contacts has been created, and whenever some new contacts are created, okay, some energy changes do occur. Okay, so here this surface you can see that is the on the interface of liquid solid. This whole surface is liquid gas interface, and this surface also you must realize that is gas solid interface. Okay, so if we take a small element dl length inside the plane of this liquid over here, so this will be experiencing a surface tension force in this direction along this interface also. So what I will be saying, that would be simply sigma, I will write it as gas solid, because this is, or solid gas, whatever you want to write. So sigma sg, or rather write it sg. Okay, So sigma Sg over here, and that multiplied with the dl. So that would be the force experienced by this element in this direction over here. And along this interface also there would be some force, and along this interface also there would be some force. So this here you can see that would be nothing but sigma solid liquid interface into dl, and this would be nothing but sigma liquid gas interface into dl over here. And now this molecule is in equilibrium, you must realize, and if this angle, which is the contact angle, that is theta, the force balance will simply give us, that would be sigma Sg will be equal to sigma SL minus sigma Lg into cos theta, you must realize. Sorry, plus here. Okay, we are taking the horizontal component, because the vertical component, in order to balance that, there would be some normal coming into the picture. Okay, so you should realize, and dl obviously is getting cancelled both sides, so you should realize the cos theta term is simply sigma Sg minus sigma SL divided by sigma Lg over here. So this gives us the value of the contact angle. Okay, and that definitely depends upon what parameters, that is the surface tension between the solid gas interface, surface tension between the solid liquid interface, and surface tension between liquid gas interface. So you should clearly realize that if sigma Sg is greater than sigma Sl, okay, so that would be, you must say, like cos theta would be positive or theta would be acute. So that is for the wetting combination. And you must realize if sigma Sg is less than sigma SL, so that would be non-wetting combination, because in that case this right hand side of this expression will turn out to be negative. So that means theta would definitely be obtuse angle over here. So this is how you can calculate the contact angle. Okay. So now let's discuss a few problems, okay, of capillary rise. Or before that, let's discuss the concept of capillary rise first. Okay, capillary rise. So let's say we have a capillary tube of, say, its radius is r, it's a capital R, and that has been dipped into some liquid. Okay, that has been dipped into some liquid. So what will happen, that some liquid will rise in this capillary tube, okay, to some height h. Okay, and this here is known as capillary rise. Okay, and this h, the expression of this h, you must remember, that is nothing but 2 sigma cos theta by r rho g, or simply you can say 2 sigma by some small r rho g. I will be explaining each and every term. Okay, so sigma definitely here is nothing but the surface tension of this liquid over here, and rho is, sigma is surface tension and rho is the density. Obviously g is the gravitational acceleration in this case. And you must realize this capital R, let me be specific, this capital R is the radius of capillary tube. This is the radius of capillary tube, this radius over here. And the small r which we have taken is nothing but the radius of meniscus. Radius of meniscus means you are seeing that this here is forming a curved surface. So this must be part of some sphere. So this radius, this, let's say, is the center of that. So this radius, I am saying it as radius of meniscus. And this cos theta, this theta term we have just discussed, that is nothing but the contact angle. So this angle here is the contact angle over there. And it is also very important that how have we got this expression. In order to realize that, two ways we can do it. Like one method is the simply the force method, and the another method is the pressure method. So let's do it with the pressure method first. Okay, so let's take one point here at the up of this meniscus, let's say point number 1, and let's take another point, point number 2 over here. So this liquid is static liquid. You must realize point 1 is exposed to atmosphere, as well as point 2 is also exposed to atmosphere. So you must realize the pressure difference between point 1 and 2 is going to be equal to 0. So if we move from point 1 to point 2 along this path, the pressure variation must be equal to 0. So you should realize from here to here, like from the concave side to convex side, when we move, so the pressure decreases. Concave side the pressure is more, convex side the pressure is less. So pressure here is decreasing. And how much would be the decrease of pressure? That will depend upon this radii of curvature, which is spherical, part of a spherical surface. So let's say we have already written r is the radius of meniscus, so that is going to be 2 sigma by r, would be the pressure decrease in pressure as we move from concave side to convex side. And now let's move from here to here, and to a depth of h over here. So that would be pressure will be increasing by rho gh, and the net pressure variation from point 1 to point 2 is equal to 0. So h simply you realize that is nothing but 2 sigma upon r rho g over here. So we have got this expression. Okay, and small r, you must realize, is nothing but capital R by cos theta. Let's look closely into the geometry, and let me draw the diagram once again. Let's say this is the tube, okay, and this is the meniscus, okay, and this angle is theta over here. And imagine this sphere, for example, its center would be somewhere here. So if we draw the R thing, so this angle is 90 degree, and looking in this right angle triangle, let's say ABC over here, so you should realize like AB is nothing but equal to R. So if this angle is theta, this angle got to be theta as well. So looking in this right angle triangle, you can clearly see that small r is nothing but capital R by cos theta. So this will also turn out to be 2 sigma cos theta by capital R rho g. Please understand the difference between these two formulas. Here small r is nothing but the radius of meniscus, and the capital R here is nothing but the radius of the capillary tube over here. So this is one method. This thing could be done using the force analysis also. Now you must realize like this. Here at this contact there would be a surface tension force, okay, in this direction, and this surface tension force, you can see, that would be sigma into the length of this periphery, which would be nothing but 2 pi r over here, and its vertically upward component, if this is theta, so its vertically upward component would be nothing but that multiplied with cos theta. So this upward surface tension force will kind of pull this liquid in upward direction until it is balanced by the weight of the rising liquid over here. So this will be equal to, you must realize, the weight of the risen liquid over here would be like the mass would be simply, you can say, density times volume, and volume would be pi capital R square is the cross sectional area, and h is let's say a rise. So basically we are ignoring this height over here, little this height we are ignoring. So this would be the mass of the water which has risen into the capillary tube, and that multiplied with g. So here the surface tension force which is acting in upward direction is balancing the vertically downward weight. Okay, so this you realize, this rearranging this will again give you this relationship over here, this relationship. Okay, so this is a very important formula. And let's now also look at the energetics of this situation. Energetics of this situation. Okay. So this is the capillary and its radius is r. We have already looked, and this has been dipped into some liquid here. Okay. So there would be some capillary rise. We have already understood that. So as I have already stated, that the surface tension force, like the vertically upward component, we have already written that would be sigma into 2 pi r into cos theta. So that would be the surface tension force. Okay. And basically this surface tension force will do work on this liquid, because it is the liquid's potential energy is increasing over here. Okay, so let's look into the energetics. So first we must try to find out like work done by surface tension force on liquid, surface tension force, and that is simply going to be force dot displacement. So this is force, so that would be sigma into 2 pi r into cos theta, and displacement of the liquid here is h. So h we have already calculated, that is nothing but 2 sigma cos theta upon r rho g. So r and r here gets cancelled. So what we are getting over here is, when we will be rearranging that, so 4 pi sigma square into cos square theta upon rho g. So this term you can see is the work done by the surface tension force. So this work done by the surface tension force will cause some change in potential energy or gravitational potential energy of the liquid, and the change in gravitational potential energy of the liquid would be mass times g into change in height of the center of mass, you must realize. So the mass obviously of the risen liquid is rho times volume, so rho into pi r square into h. Okay, this is mass into g into h again over here. So basically we have got rho into pi r square into h square into g, and the value of h we already know. So when we will be substituting that here, okay, change in gravitational potential energy, we will be getting 2 pi sigma square into cos square theta upon rho g. Now observe closely. This is the work done by surface tension force. This coefficient you must realize, that is 4, and this is the change in potential energy. This coefficient you should realize is 2. Okay, so that you must understand, like if work done by surface tension force is this much and change in potential energy is smaller than that, in fact half of that quantity, okay, so where has the remaining energy gone? So the idea is the remaining energy will be lost, okay, in form of heat, or that energy will be dissipated. So what you must realize, what is happening over here, that once this surface tension force starts pulling this liquid, so this is the equilibrium position. So over there, here the force becomes zero, but the liquid, because it will gain some velocity, now it will rise to double of height, and then it will come back, okay, and then it will oscillate about this mean position. And if there are some dissipative forces also, so due to that dissipation, okay, uh, like this oscillation will it slowly die, okay, and some amount of energy will be released also, you must realize, okay, or some amount of energy would be dissipated. So heat dissipated, let's try to find out heat dissipated in this case. That would be simply equal to work done by surface tension force minus change in gravitational potential energy. So when you will be subtracting this quantity from this quantity, you will be getting 2 pi sigma square cos square theta upon rho g. So you must realize, whatever is the work done by surface tension force, half of it is stored in form of gravitational potential energy of liquid, and the remaining half gets dissipated in form of heat. So you can expect some temperature rise of the liquid inside the capillary also. So this is the energy aspect of this situation. Another thing which I feel important to discuss over here is something like we have seen that the capillary rise is nothing but 2 sigma cos theta by r rho g. Okay, so that definitely that the capillary height should be greater than that capillary rise over here. So what if the capillary is of insufficient height? Capillary is of insufficient height. This situation let's look into. So you might feel that if the capillary is of insufficient height, then liquid will begin to overflow, something like that. So but that does not happen. You should realize that does not happen. Okay, so what happens is, okay, if this height is insufficient, let's say if this height is h, okay, and this is less than this quantity, that is 2 sigma cos theta by r rho g. If this is less than this quantity, then we are saying that this capillary is of insufficient height, because this otherwise would have been the capillary rise. So this is the capillary height. So anyway, this is less than this quantity over here. So what will happen? So liquid will push and push. Okay, so what will happen? This surface tension force, vertical component of surface tension force, will decrease. Okay, because the less liquid it has to balance over here. So here you must realize the radius of meniscus, you must realize, would increase over here. Like this is say r dash. Okay, so this will increase. Okay, so you must realize like this quantity here is 2 sigma by r rho g. So if r is corresponding to when the height of capillary would have been sufficient, okay, so this r will change. This radius of curvature of meniscus will change over here if capillary is of insufficient height, such that this quantity is equal to you must realize 2 sigma, or basically in that case h will be equal to 2 sigma by r dash rho g. Okay, r dash rho g over here. So basically you should realize that r dash would be increasing if h is less. Okay, so and also another way you can say that the contact angle would be changing. Okay, so like you can say that is 2 sigma. This quantity can also be written as 2 sigma by say something uh, r rho g, and here that would be cos theta dash over here. So theta dash over here or r dash will change itself accordingly, okay, with respect to this height of capillary, and the maximum height of the maximum rise in the capillary would be constrained or will be restricted by the height of this capillary over here. So but it will not overflow. And one another interesting case you should realize, like capillary rise in inclined tube, say inclined tube over here. So if we have a situation, let's say we have an inclined tube, let's say it is making an angle of alpha with the horizontal, let's say. So obviously the liquid will be rising in that, and we have already understood the uh, component of surface tension force along the tube, that is going to be 2 pi r into sigma cos theta over here. And now the weight is acting in vertically downward direction, so this force will be balanced by the component of weight along the tube. So that is definitely, this component would be nothing but w sine alpha. So you must realize that w sine alpha will be nothing but equal to 2 pi r into sigma cos theta over here. So and also you must realize, if say we are interested in finding out the vertical capillary height rise, like this h over here. Okay, so how much would be w? You must see. So w is nothing but the volume of the liquid would be again rho into pi r square into this length over here. This length over here, which is nothing but h upon sine alpha, and that multiplied with sine alpha will give us nothing but 2 pi r into sigma cos theta over here. And this sine alpha will get cancelled, and this pi will get cancelled over here, this r will also get cancelled. So rearranging, you will be still be getting 2 sigma cos theta upon r rho g. So you should realize this vertical rise in the height of liquid inside the capillary is still going to be same even if the tube is inclined. Okay, in fact, if the a tube is of some random shape, okay, for example this kind of shape, this random shape we are having, okay, so in that case also, like for example, liquid will rise to, so let's say some this height, and this height will be same as the previous value, that is 2 sigma cos theta by r rho g only. Okay, so vertical rise of capillary has same expression, you should realize. And one another interesting thing, like for example, all these cases we have been looking into the case when theta is acute. If theta is obtuse, if theta is greater than 135 degree, then this term would be negative. So H would be negative. So rather in place of the capillary rise, we will be having, like you can say, capillary fall. Like for example, this is the capillary here, okay, and we have submerged into the some non-wetting lick combination. So like this would be a fall in uh, like level over here, and this H here would be like 2 sigma cos theta by r rho g, and this cos theta term is negative, so you can use a mod sign over here because the this is fall already, you are taking the magnitude of H. Okay, so that is in case of the obtuse contact angle. Now let's have some problem of another model. Like we have looked into a normal capillary, and let's look into some kind of variation also. Let's have this question. Let's say we have a conical capillary. Let's say we have a conical capillary, okay, like this, and we have submerged into that some liquid. Okay, so this will rise to some height, and we are now interested in finding out like what would be the capillary rise this time. Okay, so the things that are given to us is, first of all, this apex angle of cone, this alpha is given to us, and also here the contact angle theta is given to us. And the other thing which is given to us, like this would be the circular cross section of the capillary at the contact of the meniscus, and this, let's say, r is given to us. So if all these things are given to us, like can we find out this H over here? So the idea is very, very simple. The idea here is very, very simple. We just need to find out the radius of curvature of meniscus. Okay, and we can use that formula. H is equal to 2 sigma we will not write cos theta this time, so 2 sigma simply by r rho g. Only you should notice here this r is nothing but the radius of curvature of this meniscus. You must realize radius of curvature of this meniscus. So let's say its center would be somewhere here. So this radius of curvature which we are using, like obviously we can use that formula. Remember the pressure method of finding out the capillary rise. For example, we move from here to here, so pressure decreases to sigma by r, and that would be equal to rho gh, etc. So that relationship will still be valid irrespective of what kind of shape of the tube we are having. Only here we are interested in the radius of the meniscus, so we are in trying to find out this r over here. So this r, can we find out it geometrically over here? So now let's look into this situation. So this is the axis of the cone now. Okay, and now see this angle here would be nothing but alpha by 2 half apex angle. Okay, so looking in this right angle triangle, this would be the exterior angle. So you can say that is nothing but theta plus alpha by 2. Okay, and now you see, like, this is 90 degree, and if we imagine a triangle over here, this is 90 degree, and this angle is theta plus alpha by 2. So this angle here will also be theta plus alpha by 2, where theta is contact angle and alpha by 2 is nothing but half apex angle. Okay, so here you must realize that r is nothing but, this time that would be, sorry, r would be, a small r would be nothing but capital R divided by cos theta plus alpha by 2, theta plus alpha by 2, and you can simply substitute this in this equation. So you will be getting 2 sigma cos theta plus alpha by 2 upon r, r rho g over here. So this quantity you will be getting, this quantity. Okay. Okay, and you should realize, for example, in case of cylindrical capillary, this alpha will turn out to be equal to 0, and obviously you will be getting the formula you are used to. So, but this is in case of the conical capillary tube over here. So that, I think, like, this is one of the previous year JEE problem also. One another interesting problem I want to discuss over here is, let's imagine uh, two infinite parallel plates. Let's say this is one of the parallel plate and this is another parallel plate. Okay. Okay, and the distance between them is, let's say, quite small. This distance is not very much. Let's say this is d, and this is d, this d is small. Okay, and these two parallel plates, when submerged into some liquid, there will be rise in liquid column here as well. There would be rise in liquid column here as well. And let's say you can imagine the three-dimensional view of this thing. Okay, so imagine, like, let's say this contact angle here is theta. Okay, so what would be now this h over here? Okay, so you must realize about this curvature over here. Is this a spherical curvature? No, this is not a spherical curvature, because it would be like, you can imagine, like, this would be the shape of liquid. So this is a cylindrical curvature. And you remember when we said, like, the excess pressure across a surface having two radii of curvature. Okay, and the formula was nothing but delta P was equal to sigma into 1 by R1 plus 1 by R2 over here. And I discussed this case as well. Like, see here, R1 will be equal to R, which would be the radius of this curve here, and R2 will be tending to infinity, because this is cylindrical interface. Okay, so delta P simply will turn out to be sigma upon R, not 2 sigma upon R like in the previous spherical cases. So only difference is delta P will be equal to sigma by R over here, where R is the radius of curvature of this curve. Okay, so being said that, like, from here to here, when you will go, this will be the a decrease in pressure, and that will be simply equal to rho g h over here. Okay, so h will be this time only sigma by r rho g. And obviously you must realize, like, for example, let's have some geometry here. Okay, so this would be the center of curvature of this curve. Like, so let's say this is basically R, and if we draw a right angle triangle here, okay, so this angle got to be theta, and this is going to be d by 2. So basically R, you can say, that would be nothing but d by 2 cos theta. Okay, d by 2 cos theta. And when you will be substituting this value of R over here, what you will be getting is 2 sigma cos theta by rho g d over here. So this is one of the idea. Okay, so that is delta P, and I think like our time is up now. So here in this class, okay, we tried to look into the capillary rise thing, and in the next class we will be starting elasticity. Okay, so that's it for today. Thank you very much for joining.